Our general statement of Ampere's law is that the line integral of B dot ds around a closed path is equal to how much current is enclosed in that path. And so if we have an enclosed path, and we have a circulation direction, and we have I, for instance, here, that's out of the plane of the figure, then we know that this integral will just be equal to mu naught I. And if there was current outside, we don't have to include that in Ampere's law, even though all of these currents, let's call it I1, I2, and I3, all of these currents are producing the B field. So all currents are sources of the magnetic field, of the B field. And that sometimes confuses people on Ampere's law. But in terms of what the actual integral is equal to, it's only equal to the I enclosed. Now, how are we going to prove this general result? We'll do it in two stages. What we want to first prove is that if the current lies outside our, I'll call this our Amperian loop. If a current lies outside our Amperian loop, this integral will be 0. We've already shown for a circle that this holds if it's a perfect circle and the current is centered in the circle. And then we'll want to show some arbitrary shape like this that the theorem still holds, that a physical law still holds. So our first case is, let's consider this. Let's have a current I, which is out of the plane of the figure. And let's consider a path, our Amperian loop. And I'm going to draw some radial lines like this. And our loop is going to consist of a radial leg, like that. So this is a distance R1. That's a tangential leg, a radial leg outwards, another radial tangential leg, and a radial leg inwards. Out here, we're at R2. So I'm going to consider this as my Amperian loop. And I'll use this as a very long, again, an infinite wire, where the B field magnitude is mu naught I over 2 pi r. So when we integrate, and remember this field, if we chose our coordinate system, r hat, theta hat. So now we notice that we have 4 legs to calculate our line integral of B dot ds around these 4 legs. Now, the line elements, notice that on this leg, the B field is in the direction of the line element. Over here, the B field is going to be perpendicular to the line element, so there's no contribution. This one is interesting because here's the line element. That's the B field. In this case, the line element is this way, but the B field is the opposite direction, so we're going to have a negative sign. And over here, again, our B field is perpendicular to the line element. So on these 2 legs, there's no contribution, positive, negative. And now let's look at the, if we call this some angle theta, then the length of this leg, since B is tangent, and the length of the leg is just the arc length, which is the radius times the angle, we see on the positive leg, we get mu naught I over 2 pi, we're a distance r2 away, times r2 angle theta. And on this leg, it's negative, so we get minus mu naught I over 2 pi r1 times the same angle, r1 theta is the arc length. And you can see that because the B field goes like 1 over r, and the length of the path goes like r, these 2 effects cancel. And that's precisely why when I is not enclosed inside the Amperian loop, in this very particular loop, that the line integral of B around a closed path is 0. Now, if we want to extend this argument to an arbitrary loop, let's look at I. This requires what we can call a deformation of the path. We know if we vary the path just a little bit as we go around this loop, we can deform our path continually from what we had earlier, a little tangential, radial, tangential, radial, tangential, radial. And so effectively, under these small deformations of the path, we can take our nice, clear path here and deform it to an arbitrary path. And our result now is that the line integral of B around a closed path, if there's no current that cuts through the path, then the line integral is 0. And that's the second part of our proof of Ampere's law. Now we want to put it all together to prove Ampere's law in general for an arbitrary path that does contain current. We would now like to look at a general case for Ampere's law. B dot ds is mu naught times the current that cuts through a plane defined by the area defined by our choice of a closed path. Now here we're going to have not a circular path, but this will be an arbitrary closed path. Now, in order to show this result, let's consider a very special case. Let's begin with a current I that's not enclosed in a very particular path that I'm going to choose. And here's the path I'm choosing. I'm going to do a circle, and then I'll go up like that. I'll have an arbitrary path on the outside. I'll come very close to that line, come back, and continue the circular path. Now, this will be my arbitrary path on the outside, as you'll see in a moment. Now, I can think of, when I do this line integral, first off, we know right away from Ampere's law, because I is not enclosed in this area defined by the closed path, that for this particular case, we've already shown that the line integral of B around this closed path is 0. Now, here comes the interesting point. When I take this line integral going out or coming back, and they're very close together, so this is a very, very tiny distance, you can call it epsilon, that the contributions of those two legs will cancel because I'm going in opposite directions. So what I'm left with is a circular path. So let's draw I. I'm left with this circular path, and notice this is my circulation direction. We'll get to that in a moment. These two parallel legs next to each other cancel, and I'm left with, I'll try to draw something that looks like our arbitrary path on the outside, and that was the outside path. This is the arbitrary path. Now notice I'm circulating that way on my arbitrary path, and my goal is to figure out what the line integral of B is around this path. Well, now remember circulation directions. When our current I is pointing in this direction, but we're circulating like that, then by the right-hand rule, according to our circulation direction, the right-hand n-hat right-hand rule is pointed opposite the direction of I. And this means that this integral here is equal to, this is a circular path, call it radius r, is minus, because I is opposite our consistency with our circulation direction, so it's minus mu naught I. And over here, this is our objective, B dot ds around our arbitrary path. And because these two things are equal to 0, because I is not enclosed, we now conclude that B dot ds around an arbitrary path, and not just a circular path, is equal to, we bring this to the other side, is equal to mu naught, and I is the I enclosed, and so there we are. We've shown the general case for Ampere's law.